Good afternoon. How's everybody? 8 students in here. I think the computer clock is right. 1:30. I have 1:30. So today's lab. Thank you. I'm well. Good afternoon. Cool. Today's lab is let me show you the syllabus. So today's lab includes topics and concepts that are have not yet been taught in my lecture. I went through the attendance or the roster for this lab, and there are most of the students are in my lecture. I think there's like 5 or 6 that are in another professor's lecture, and I believe that they have they've gotten to the concepts for this lab, and so therefore I've made I'm going to do the lab this week, but then I'm going to do the lab again next week for the students that are in my lecture. And so for those of you that are in my lectures, you have the option of staying in this one or the next week one. But I think it's important to teach it I think it's important to teach it today, because those that are in the other lecture will benefit from doing this lab before they take their exam, their midterm exam. I'm gonna teach this lab again next week because it'll be right after my midterm exam, which would be a perfect time to teach it. Anyway, that said, you guys have the option. I recommend sitting through both, actually. But if you have Professor Reese, I think is the other professor. If you have Professor Reese, I would definitely stay in this lab today because you'll benefit. All right. Any questions about that? Cool. So let's look at the lab manual. My computer. So this is empirical formula. So everyone knows what an empirical formula is. I believe it's smallest whole number ratio of atoms, of the smallest whole number ratio of atoms in a compound. Right. So we learned about empirical formulas, and ionic compounds are basically empirical formulas. Ionic compounds are basically empirical formulas. They're governed by the charges, right? And so I want to whiteboard and teach a couple of concepts. So a couple of the concepts that may be new to some students, may not be, include, oh, let me grab my periodic table first. Should have had my periodic table handy. Where is it? There it is. All right, now I have it. All right. So the periodic table has the atomic masses, right? An atomic mass unit. So we've looked at the average mass, the average atomic mass in lecture. And so this number with the decimal, the long decimal, that's the average atomic mass. So let's look at the average atomic mass, and I'm going to compare it to the formula mass, and then we're going to talk about something called the mole and the molar mass. And then we're going to get into calculating an empirical formula. So we're going to do 3 things. I'm going to, by way of introduction to this lab, we are going to cover the concepts of atomic mass, formula mass, molar mass, and then we're going to calculate empirical formula. Uh-oh, my calculator fell. No, what fell? What is this? Oh, my textbook's falling apart. Calculate empirical formula. All right, so first I'm going to do the atomic mass. So the atomic mass, let's just for, we'll use carbon. What is the atomic mass of carbon? Carbon, not carbon, carbon, right? C, and if we look on the periodic table, does everyone have a periodic table? You should have a periodic table out. Should be handy. I'll go back to the periodic table. And so we have like all these numbers, 12.0107. All right, so typically I'll just always use 4 sig figs. So if we just, so that's a good rule of thumb to take 4 sig figs, because normally like most significant figures, most calculations, you'll end up with like 3. And then so if you 4, that should be more than enough in any calculation you need to do. So whenever you take an atomic mass from the periodic table, 4 sig figs is a good way to go. So I'm going to write 12.01. I think that's a good rule of thumb. Doesn't require much thought. And so for carbon, the atomic mass is 12.01 atomic mass units. So the formula mass would be if you have like a compound. And so let's do a formula mass for, how about, I was going to do water. Let's do methane. Formula mass for CH3. CH4, I'm sorry, methane. So methane is CH4. And so what is the formula mass? Well, it's going to be the atomic masses all added up, right? So for 1 carbon, that's going to be 1 times 12.01 atomic mass units equals 12.01 atomic mass units. For 4 hydrogens, that's going to equal 4 times 1.008 atomic mass units. That is equal to 4.032 atomic mass units. I'll just allow my units to carry down. So we have a 2, a 4, that's a 4, a 0, 6, 16.042 atomic mass units. Any questions about atomic mass versus formula mass? All right, so let me talk about the mole. What is the mole? The mole, abbreviated MOL, is a number, right? So it's a number. So the mole is a number used for counting very small things. Like, for example, a dozen is a number, it equals 12, right? So a dozen is a number is equal to 12. The mole is a number, so a mole, if we want to keep the, so a mole is a number, and it's a very, 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 very large number. And so I'm not going to write it out completely. 6.022 times 10 to the 23rd. Why is it so large? It's because it's used to count very, 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 very small things, right? Things that are incomprehensibly small. We can't even really, it's hard to picture how small these things are. So we use a mole when we're talking about atoms, molecules, ions, electrons, things like that, things that are super, super, super small. We'll see in chapter 6, we'll talk about photons. So these are really, really small objects. Very, very small things. Very, very small things. Like we use a dozen when we're talking about eggs, right? I got a dozen eggs, right? I have a dozen donuts, right? I went to Costco the other day and I got 2 dozen eggs, right? So rather than saying 24, I say 2 dozen. And so it's useful in that way. So a mole is used, and it's a very, very, very small number. So it's unitless, right? It's just a number. And so we'll refer to things as moles. Like I might have a mole. If I have 1 mole of carbon, that means I have 6.022 times 10 to the 23rd carbon. And then we can put anything here, right? 1 mole of carbons and atoms. So if I have a mole of carbon atoms, I have 6.022 times 10 to the 23rd carbon atoms. Does that make sense? So it's a mole. So it's a very, very small number because atoms are it's a very, very large number because atoms are very, very, very small. Now, if we go back to our atomic mass and formula mass, we can express the what's known as the molar mass, right? So if I use the molar mass, I'm going to kind of do a jump here. I'm just going to tell you the units. So I'm going to tell you the units. So the molar mass is like the same as the atomic and the formula mass, but instead of using units of AMU, the units will be grams per mole. So let me show what I mean by that. So the molar mass of carbon is equal to 12.01 grams per mole. The molar mass for methane is equal to 16.042 grams per mole. So what does that mean? This you should recognize this as a conversion factor. That means that 1 mole of methane, we'll go with the methane example, 1 mole of methane weighs 16.042 grams. Or 16.042 grams of methane. That's grams. Oh, that's supposed to be a 4. (16.042 grams of methane is equal to 1 mole of methane. So now this is a very practical unit, right? The molar mass is much more practical. So it allows us to convert from a count of how many molecules. So we could say, let's bring this out. We can if I follow this logic here, if I bring this out here, I could say that 16.042 grams of methane is equal to 1 mole of methane, and that is equal to 6.022 times 10 to the 23rd methane molecules. And so this mole is a very practical unit, right? It allows us to count things. And then so now when we look at the periodic table, we should think of the periodic table as being listed in molar masses because it's a much more convenient unit. It allows us to go from a mass to a count, right? From how many to how much does it weigh. So it's very practical. Any questions? All right, so let's do an example. Let's do an empirical formula example. I'm going to jump right to the empirical formula. I have an empirical formula example right here. It says ethylene glycol. Ethylene glycol. It's used in antifreeze, right? They make it green. It's actually colorless. Ethylene glycol is 38.7% carbon, 9.7% hydrogen, and 51.6% oxygen. What is the empirical formula? All right, so the empirical formula is the smallest whole number ratio, right? So so we're looking for CHO, but we don't know the subscripts X, Y, and Z. So, but it's going to be we want the smallest whole number ratio. The empirical formula is the smallest whole number ratio. Ratio, no N. And so we can think of this as atom to atom, or we can think of this as, we can think of the ratio of X, the subscripts to Y to Z, as atom to atom, atom to atom, or a much more useful way to think of this, the empirical formula, the X to Y to Z, and it's both as accurate, is as mole to mole, mole to mole. It's much more useful, and it's legitimate, right? It's legitimate because if it's atom to atom, we're just multiplying the number of atoms times 6.02 times 10 to the 23rd, and you get the number of moles, right? So when you think of an empirical formula or a molecular formula, you should think of it as a mole to mole ratio. So a molecular formula is a mole to mole ratio, as well as an atom to atom ratio. The empirical formula is the smallest whole number mole to mole ratio. And so with that knowledge, it should make it easy to solve this problem. And so we have ethylene glycol. It tells us the percentages of carbon, hydrogen, and oxygen. Those that should add up to 100%. I'm sure it does. So that's 100%. And so I'm going to solve this problem, I'm going to assume a 100-gram sample. By assuming a 100-gram sample, that's a fair assumption, right? I assume a 100-gram sample of ethylene glycol. Let me write of ethylene glycol. Of ethylene glycol. And now I can express these percentages as grams, because 100 grams, 100%, right? So this would be 38.7 grams of carbon, 9.7 grams of hydrogen, 51.6 grams of oxygen, right? So that's what assuming a 100-gram sample is. So, and so now I can express percentages. Let me write that out. Express percentages as grams. All right, so now what I'm going to do, I'm trying to get the empirical formula. I want the mole to mole ratio, so I'm going to convert so convert from grams to moles. And so how do we convert from grams to moles? We use molar mass. So you should have your periodic table handy. And so let's do this. So carbon, 38.7 grams of carbon. I'm going to convert that to moles. And the periodic table tells me that 1 mole of carbon weighs 12.01 grams. You guys with me? 12.01 grams. And so, yep, cool. All right, so get your calculator out. 38.7 divided by 12.01 equals, I get 3.222 moles of carbon. All right, let's do hydrogen now. 9.7 grams of hydrogen. 1 mole of hydrogen weighs 1.008 grams right? It's a conversion factor. Molar mass, the molar mass from the periodic table. So 9.7 divided by 9.7 divided by 1.008 equals 9.623 moles of hydrogen. Finally, oxygen, 51.6 grams of oxygen. 1 mole of oxygen weighs 16.00 grams. Prove it on a periodic table. 4 sig figs, 51.6 divided by 16 equals 3.225 moles of oxygen. All right, so now we have the moles of carbon, the moles of hydrogen, and the moles of oxygen, and they correspond to like the X, Y, and Z in these subscripts up here. However, we want the smallest whole number ratio, right? So we want one of them to be 1, right? So if I make one of them 1, right? So these are ratios to each other. So if I divide all of these numbers by the smallest number, so the carbon has the smallest number, so 3.222. So if I divide by that, let me double check those numbers. That seems weird. 38.7 divided by 12.01. Yeah, 3.222. All right, so I'm going to divide all of these numbers by the smallest number. So for example, for carbon, let me switch colors. So for carbon, 3.222 moles divided by 3.222 moles of carbon is equal to 1, right? So that makes sense, yeah? So carbon is so that's the smallest whole number ratio of carbon. So carbon is going to be like our smallest one. It is the smallest one. All right, so what about hydrogen? So for hydrogen, 9.623 moles of hydrogen divided by 3.222 moles of carbon. Put that in your calculator. 9.623 divided by 3.222. I get 2.99 moles of hydrogen to carbon. So the moles of hydrogen to carbon which is approximately 3. So for every 1 mole of carbon, I have 3 moles of hydrogen. That's okay, yeah? You guys with me? And then so for oxygen, I think we can see that 3.225 moles of oxygen for every 3.222 moles of carbon. So we always use the smallest one. We divide them all by the smallest, whatever the smallest one is. It happens to be carbon this time. This is going to come out to be 3.225 divided by 3.222. I get 1.00 moles of oxygen per mole of carbon, which is 1, equals 1. All right, so now my empirical formula in pink is CH3O. CH3O. So the empirical formula is 1 carbon atom to 3 hydrogen atoms to 1 oxygen atom, or 3 moles of carbon to 1 mole of carbon to 3 moles of hydrogen to 1 mole of oxygen, 1 to 3 to 1 to 3 to 1. That's the empirical formula for ethylene glycol. And I happen to know the structure of ethylene glycol is this. So you can see there are 2 carbons, 6 hydrogens, and 2 oxygens. So this is the molecular formula. And you can see that it's in the ratio of 1 to 3 to 1. So our answer is right. So it checks. So this is how you use experimental data. You use experimental data to determine the empirical formula. Any questions? So in today's lab, what are they doing in today's lab? We're going to determine the empirical formula for magnesium chloride. So the empirical formula for magnesium chloride, I'll find it here somewhere. There it is. So your book does an experiment here, does an example here of aluminum oxide. Similar example to what I did. Theirs doesn't come out to exactly whole numbers when they do the division, right? And so they get 1.5 to 1. And so they end up having to multiply by a factor to get whole numbers. I have an example in my book that comes out like 1.3, and so you have to multiply by 3. This one you have to multiply by 2. Anyway, so the experiment, we're going to figure out the empirical formula of magnesium chloride, right? The empirical formula of magnesium chloride. And so you're going to have a strip of magnesium and you're going to weigh it, right? So we'll have the mass of magnesium. And once you have the mass of magnesium, it's easy to convert it to moles, right? So you have the mass of magnesium, and then it's easy to convert it to moles just by using the, oh man, what this thing keeps, you could just use the molar mass of magnesium, 24.31 grams per mole, right? So 24.31 grams to mole. So once you have the mass of magnesium, easily convert them to moles, and that number is going to stay. Now, the weight of the chlorine is going to be determined experimentally, like indirectly. The weight of magnesium is determined experimentally just by weighing it, and so it's kind of solid. That's not going to change. But the weight of the chlorine is going to it has potential to change. So let me show you what I mean by showing you the reaction. So we're going to take magnesium solid. It's a strip. It's a metal, so it's a shiny silvery solid. And then we're going to react that with 6 molar hydrochloric acid, HCl aqueous. So this is 6 molar, which is a concentration. So it's pretty strong. So what hydrochloric acid is hydrogen chloride dissolved in water. So it's hydrogen chloride dissolved in water. And so when you put hydrogen chloride in water, it's a strong acid. And so you're going to have hydrogen ions and chloride ions surrounded by water molecules. The aqueous shows you that it's surrounded by water molecules. And so 6 molar refers to the concentration. We'll get to that at the end of chapter 3. It doesn't need to be brought up here. Let me write it though. 6 molar. And this is a concentration. And so what happens with this reaction, you're going to see bubbles. You're going to see bubbles. What's happening with the bubbles is in this reaction, you're going to be evolving hydrogen gas. Hydrogen gas, you're going to see bubbles when you do this reaction. Bubbles, so hydrogen gas is going to come out. And then you're going to make magnesium chloride. And we're trying to find the empirical formula for magnesium chloride, right? But we already know, because we studied chapter 2, we know what the empirical formula of magnesium chloride is. Who's going to tell me what the empirical formula of magnesium chloride is? What is the empirical formula for magnesium chloride? All right, so let's figure it out. I didn't have to move. I want to go over here. All right, so magnesium is +2, right? Because it's in the second column. These guys are +1. And then chloride is -1, right? So we already know the empirical formula, right? The empirical formula for magnesium chloride has got to be, well, if we have Mg2+ and chlorine minus, right? There you need 2 chlorides for every magnesium, so it's going to be MgCl2. So we already know the answer, right? We know what the answer is supposed to be, but we're still going to do the experiment because this is more about doing the experiment than calculating the empirical formula, more or less. All right, so we know what the answer is supposed to be. And so we know the mass. So this is going to be a mole to mole ratio. We should have 1 mole of magnesium to every 2 moles of chlorine. That's what the answer should be. That's what we're striving for, right? If we do our experiment perfectly, this is what we should get. All right, so we have we got the mass of magnesium, so we have the mass, we have the moles of magnesium already. The only thing we don't have is the moles of chlorine. How do we get the moles of chlorine? Well, we're going to get it from the mass. So we're going to get our product. Here's our product. And so we have to, the product is going to be wet because this is in water, right? This is going to be aqueous. This is aqueous. So the hydrogen goes away, and so we're just left with our product. But when we have our product, when we have our product, we're going to have magnesium chloride, aqueous, aqueous. So that means we have magnesium chloride. There's going to be water. That's what the aqueous is. And there's going to be leftover HCl. There's going to be leftover HCl. And so we're going to cook this thing. We're going to cook it until it's dry. And so when we cook it, we're going to use a flame. Our product's going to be in here. We're going to use a flame. That's a flame to evaporate the water. And the first thing that's going to leave is the HCl. We're going to do it in a fume hood because the HCl come off first. And it's irritant. It'll bother your eyes and your nose. And so we do that in a fume hood. So the HCl comes off first, and then the water, and then so we should be left with just dry magnesium chloride. And so we could weigh, right? So we can weigh the magnesium chloride, and then so get that mass, right? Weigh the magnesium chloride. And so we have the mass of magnesium chloride. And if we subtract the mass of the magnesium, then we'll just have the mass of the chloride. And then we can convert that into moles of chloride. And then we should have the mole to mole relationship. Does that make sense? So that's what we're going to do in the lab. All right, you have the mass of magnesium right from the get-go, right from the start, because we're going to weigh this. And then we're going to do this reaction until all the magnesium reacts. We're just going to keep adding acid until all the magnesium reacts. And so the magnesium, the moles of magnesium is kind of established based on its weight, and it's going to completely react. So now we just need to find the mass of mass of chloride and then convert it to the moles of chloride. And so by doing that, we're going to get the mass of the product, evaporate the water and the hydrochloric acid, the excess water, and then we'll just have the only problem with this whole process is in the evaporation stage. In this evaporation stage, the magnesium chloride it has the potential to sublime. So if we overheat it, this magnesium chloride can sublime. What does it mean to sublime? It means it'll go directly from magnesium chloride solid to magnesium chloride vapor. And then we lose it. So there's a potential if we overheat this. So we want to get rid of the water and get rid of the extra acid, but we have to make sure it's dry, but we don't want to go too far where we start to lose our product. Does that make sense? because we're going to use the mass of the product to determine the empirical formula, right? The empirical formula, we know the empirical formula should be empirical formula should be MgCl2, right? It should be MC, right? That's what it should be. If it is too wet, so if we don't dry it completely, right? If we don't dry, so we're going to do the experiment and then we're going to weigh it. Like it looks dry, and so we're going to weigh it. And so that's, if you look at the sheet, there's going to be many lines for the weight of the product. There'll be many lines for the weight of the product. So it'll be like mass of product, and there'll be many lines. And so you weigh it, and then once you weigh it, you kind of do your calculations and you kind of see where you are, right? But if it's too wet, right, if there's too much water in here, if there's too much water, that means there's going to be, when we weigh it, the mass is going to be too high. And so if the mass is too high, when we subtract the mass of the magnesium, the mass of the chlorine is going to be too high. And so the moles of the chlorine is going to be too high. And so if it's wet, if product is wet, right, everything's going to be too heavy. And so our estimated empirical formula will have more chlorine. So it'll be closer to magnesium chloride 3, right? We'll have too much chlorine in there. However, if we sublime it, what happens if we sublime it? If we sublime it, right, and then we lose our product, so the weight of the product is going to be low. If the weight of the product is low, and then the mass of the, so when we subtract the magnesium, the mass of the chlorine will be low, and then the moles of the chlorine is going to be low. And so if mag chloride sublimes, then the empirical formula might be too low. It'll be on the lower end, right? It'll be on the lower end, right? It's supposed to be, so this is what it's supposed to be. We know what it's supposed to be because we studied ionic compounds, right? We know the charges plus, so this is what it's supposed to be. And so if it's wet, right, from our calculations, our estimated weight of the chlorine and the moles of the chlorine will be too much. If we go too far and we sublime it, it'll be too low. And so our estimated empirical formula will be in this direction. And so you're going to check it. So you're going to take your mass, your first mass, and then you'll check, you see how close you are. Because you know what the answer is supposed to be, right? You have the moles of magnesium, and so you know it should be 2 to 1, right? If it's too high, if it's like 3 to 1, then you're going to heat it again, right? But if you go like too low, if you heat it like, and you heat it and you go too low and you get it like, it's like if your mass of if your moles of chlorine to magnesium is closer to like 1 to 1, like 1 mole of magnesium to 1.5 moles of chlorine, you know you've went too far. And so you're going to have different numbers. And so when you calculate your empirical formula, you're going to use the best choice. Does that make sense? Whichever one is closest to 2 to 1. Yeah? All right, let's look at the sheet. Cool. So the sheet is, where is it? There it is. All right. So you're going to get the weight of the magnesium. And so all these numbers are going to be generated. Watch the video. I'll put the video up. So here's the weight of the dish, which is calculated from your student number. So you'll get the weight of the dish, weight of the dish, weight of the dish. So when you're doing the lab, we're going to heat the dish several times until we have a consistent weight. So hopefully, so in this scenario, just use the last weight of your dish. So picture you're heating it, and heating it. And so use the third one. So when you're using so what do we write over here? We put that number there. So that's going to be the weight of the dish. And then the weight of the dish plus the magnesium, right? That you just write that there. And so to get the weight of magnesium, just this minus that, right? This minus that. And show your work, right? Show your work where it says weight of the magnesium. Show your subtraction. Line it up. Show me the decimal places. You know the proper numbers, decimal, right? 3 decimal places, 3 decimal places. Your answer should have 3 decimal places. Show that work. Don't just put the answer. Show the work right here. It says show all work. All right, now we're going to skip to the moles of magnesium. Skip to the moles of magnesium because this is an easy calculation, right? You're going to take the mass of the magnesium, divide it by the molecular weight. Use dimensional analysis. Show me 4 sig figs, right? Show me the unbalanced, right? The unbalanced. So you're going to take the mass of magnesium, this number right here, and then use dimensional analysis by, you know, you're going to divide by the molecular weight, the molar mass of magnesium, 24.01 or whatever it is. And then you're going to have the moles of magnesium, and you're going to show me the unrounded, right? And then you're going to put the proper number of significant figures. All right, so those two are taken care of, right? Those they're going to stay. Those don't change. And then you're going to heat the product, right? You're going to drive off watch the video, you generate these numbers, and then for each of these numbers that you generate, you're going to use the one, whichever one gives you the best ratio, whichever one gives you the best answer. So use whichever gives best answer. And so you'll get the mass. So this is the dish plus the product. So the dish plus the product minus the dish and the magnesium will give you the mass of chlorine. So this number right here, right? This number minus this number, this minus that one, will give you the mass of chlorine. Does that make sense? Because the dish and the product minus the dish and the magnesium, you're getting rid of the dish by doing that subtraction. You're getting rid of the magnesium. You'll just be left with the chlorine. And then so this will give you the mass of the chlorine. And then so don't write this number in yet. Don't write that number in here. You're going to use this for scrap, right? You'll have like a mass of chlorine converted to like moles of chlorine. And then you're going to see and then divide by moles of magnesium. I take your mass of chlorine and then convert to moles of chlorine, and then take your moles of chlorine, divide by moles of magnesium, and whichever one is closest to, right, closest to 2, whatever's closest to 2, because it's supposed to be 2 to 1, right, MgCl2, whichever one is closest to 2 from these 3 numbers, 1, 2, 3, that's the one that you write here. That's the mass that you use. And that mass that you use goes here. And then you show me the calculation. Now you show me the proper calculation, just like we did moles of magnesium for the moles of chlorine. 35.45, I believe, is the molar mass of chlorine. And you calculate the moles of chlorine. And then you show me the empirical formula, which is just the moles of chlorine divided by the moles of magnesium. That's the empirical formula. And you could say, you could write what it is, roughly, approximately. So you could write what it is actually, right? Actually, and then you say, oh, it's supposed to be this, right? You know it's supposed to be, right? You know what it's supposed to be. And then you're going to calculate, this is one different, the theoretical weight of chlorine required to react with the magnesium. I'm going to help you do this one right now. So the theoretical weight. So we know the mass of magnesium. So I'm going to set this up. So you're going to take the grams of magnesium, right? So you're going to have some kind of number, which is grams of magnesium. And so we're trying to get the grams of chlorine. And so we're going to go through this whole long process. So the grams of magnesium, and so we're going to convert that to moles of magnesium. And so how do we do that? We say 1 mole of magnesium is equal to, I don't have a periodic table handy. Oh, do I right here? I think it fell on the floor. Oh, I have one right there. 24.31 grams, right? So 24.31 grams of magnesium, right? So then our grams of magnesium cancel. And so this is the number that is from your experiment up there, right? This number is from up there. And now we're in moles of magnesium, And then we know that we know what the molar mass is supposed to be. I mean, the empirical formula is supposed to be, right? The empirical formula is supposed to be MgCl2, and this is a mole to mole ratio. This is a mole to mole ratio. So I could say that 1 mole of magnesium is equivalent to 2 moles of chlorine, according to this mole to mole ratio, right? According to the empirical formula that we know it should be. Does that make sense? So the moles, and so now we're in moles of chlorine, and then we want the theoretical grams of chlorine. So 1 mole of chlorine weighs 35.45 grams. And then the moles of chlorine cancel. And now we've calculated the grams of chlorine that is supposed to react, right? So this is what is supposed to react with our mass of magnesium if we did our experiment perfect. If we did the experiment perfect, this is the number that we should get, right? But this is a theoretical yield. And so we're going to do so we have to compare what we're supposed to get compared to what we actually got. And here we use the percent error. And the percent error, I believe, it's going to be the actual minus the theoretical divided by the theoretical. So these are masses, and then take that whole thing and multiply it by 100%. Let me check, let me make sure I got that formula correct. Yeah, experimental, theoretical, yeah, all right, good. So your actual mass of chlorine would be right here, right? That's your actual mass of chlorine. Theoretical is what we just calculated right there, right? So we started this with our mass of magnesium, right? We start that with our mass of magnesium. And then we divide by our theoretical and times 100%. And it might be negative, or it could be positive. It's okay to be negative or positive. So again, show me the unrounded answer. So this is going to show me the unrounded, right? Unrounded answer. And then show me the correct number of significant figures. And with a calculation like this, where you're going to lose your sig figs is in the subtraction, right? So you lose the sig figs in the subtraction. That'll generally determine the number of sig figs that you can use here. And so it could be positive or it could be negative. It tells you the direction. Like if you're too low, like if your actual is low, then it'll be negative, I believe. If your actual is too high, then the error will be positive. So show your sign, right? Show the sign of the error, whether it's positive or negative. And then there's a whole bunch of questions, and I think you should have no problem doing any of these questions now that I've shown you any questions? So I'll make this due in 2 weeks. You have 2 weeks. I encourage you to come next week if you haven't come today, right? Especially for my lecture students. We'll be learning this topic after our exam on Wednesday. Any questions? All right. I'll start grading stuff. And have a great Thursday. Today's Thursday, right? Be well. Email me if you have any questions or any problems. This lab is due in 2 weeks. You're welcome. See you next week, Thomas.
Thank you, Professor.
You're welcome.
Thank you, Professor.
I'll put that video up.